Hello, and this is the video for section 9.1. So here is the homework for the whole chapter 9. You can find it on PowerSchool as well, but notice that they have the required. These I didn't actually put on PowerSchool because I didn't want to confuse the issue, but yeah, some additional optional exercises for extra practice that go above and beyond what I require. But those are just a good idea in preparation for the AP test. All right, so here we're going to be talking about, we've been talking about confidence intervals, but we're basically going to be talking about testing for whether something is a, a good hypothesis or not. So um, let's just go ahead and get started. So significance tests, the basics. So if we're looking at this, um, by the end of this section, you should be able to state what the null and alternative hypotheses for a significance test about a population parameter. Remember, a population parameter is talking about the actual mu, the actual mean of the population, or the actual p, right, the proportion of the population, and then interpret a p-value. This is a different thing than the p I just talked about in state. Determine whether the results of a study are statistically significant and make an appropriate conclusion using a significance level, and interpret a type 1 and a type 2 error in context and give a consequence of each. Okay, so um, confidence intervals are one of the two most common types of statistical inference. So when your goal is to estimate the parameter based on a a sample or something like that, that's when you're going to use a confidence interval. The second common type of inference is called significance tests. So it's a different goal to assess the evidence provided by data about some claim concerning the population. So basically, trying to validate whether a hypothesis is accurate or not. So a significance test is a formal procedure for comparing observed data with a claim, again, also called a hypothesis, whose truth we want to assess. The claim is a statement about a parameter, like the population proportion p or the mean mu. We express the results of the significance test in terms of a probability that measures how well the data and the claim agree. So it's basically if somebody makes a claim and then we have data, we want to say, does the data support that claim, or does the data reject that claim, support some other conclusion than the claim. So we use it all the time as far as like whether a new drug is used or something like that. Currently with COVID-19, there it would be talking about in an experiment giving people medicine or a vaccine and giving the another a group placebo, and then trying to determine whether it's statistically significant if there's any difference or not. So we use it all the time in clinical trials and things like that. All right, so let's just do an example here. So a basketball player claims to make 80% of the free throws that he attempts. We think he might be exaggerating. To test this claim, we'll ask him to shoot some free throws virtually, and we're just going to see what happens. So let's just see what happens if he shoots 25 shots. So 80% is what he claims to make. So let's shoot 25 shots. So as it's going through here, it looks possible so far. Okay, well, he hit 60%. That's you know, below his average, but do we think he's lying? I don't know if I see enough to conclude that. Let's do another 25 shots, see what happens. Well, now I'm starting to think, well, maybe he is lying because look at all these misses. It's still not a huge sample size, but it's not making his case look real good. So let's just see what the actual probability was. It looks like it might be like 50 or 55%. So let's just take a look. Okay, it looks like the actual probability for this guy was 55%. So so I would say that would be not true, right? Rejected. So in this case, the claim was that the shooter shoots 80%. That is called the null hypothesis. Okay, the claim is, you can think of it as the null hypotenuse, hypothesis H naught. All right, so um, eh, we in this case we would reject that hypothesis because it does not look like he shoots 80%. And we're going to talk about how we can decide whether to reject that or not, just without just looking at it. So, again, a significance test starts with a careful statement of the claims we want to compare. The claim we weigh evidence against in a statistical test is called the null hypothesis. So again, we're just saying that that claim um, is what we're testing. So often the null hypothesis is a statement of no difference. So in the case of testing a new drug or something like that, that might be the null hypothesis is no difference. So the claim about the population that we are trying to find evidence for is the alternative hypothesis. So in the free throw shooter example, for example, our hypotheses are the null hypothesis is that the p equals zero point 0.8. Our alternative hypothesis, A sub A, is the probability is less than 0.8, where p is the long run proportion of made free throws. So in any significance test, the null hypothesis has the form um, where the parameter equals a value. So the null hypothesis is that this is true, right? This equals this. The alternative hypothesis can either say, well, the parameter is less than the value that's stated, it's greater than the value that's stated, or if it's either side, we could say not equal to the value. So to determine the correct form of the alternative hypothesis, read the problem carefully. So these two right here, are called one-sided hypothesis. So if we say it's larger or smaller than the value, those are one-sided. If we say it's just not equal to, so it could be larger or smaller, then that's two-sided. So stating hypotheses. The hypotheses should express the hopes or suspicions we have before we see the data. It is cheating to look at the data first and then frame hypotheses to fit what the data show. Now this is actually something that happens way too much in real life. And it has a term called p-hacking, and you'll see why in a second. But it's basically just looking for things that are statistically significant in the data without having the hypothesis ahead of time. So if we have enough data, if we look at enough different things, we're going to find something that looks like it's statistically significant, whether it is or is not, just by the sheer choice of things we can manipulate. So sometimes people will run a study, look at the data, and just um, manipulate the variables and things like that that they're looking at until they get something that's statistically significant, and that is the incorrect way of doing that. You're much more likely to find something that's misleading that way than if you do it the correct way, which is before we see the data. Hypotheses always refer to a population, not to a sample. So H naught and H sub A are in terms of population parameters. So they're in terms of mu, or P naught, X bar, or P hat. It is never correct to write a hypothesis about a sample statistic. So, I guess there we go. So again, it's not P hat or X bar. We don't want to do that. It has to be mu or P or things like that. All right, so here's an example. At the Hawaii Pineapple Company, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. They wonder how this change will affect the mean weight of pineapples grown in the field this year. So state the appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. So the parameter of interest is the mean weight. So again, I don't want to just read the solution, but so the parameter of interest, it was 31 ounces. So when we're looking at that, mu is the parameter of interest. So and they go ahead and state it all. You would want to write something along those lines in your actual answer. So a brief summary. The mean weight mu is the parameter of interest. All right. So and then our null hypothesis is basically that the mean weight is unchanged. So, and our alternative hypothesis is going to be that it's either gone up or gone down. So it's a two-sided hypothesis. So if we're looking at this, we're going to say the null hypothesis is mu equals 31. The alternative hypothesis is that mu is not equal to 31. So Again, like we said up ahead, a lot of times um, the the null hypothesis is just um, of no difference. So we noticed that happened in this example right here. So we want to know if there was a difference, and if it was likely, caused by the irrigation system. All right, so back to the basketball player. Suppose a player claimed to be an 80% free throw shooter. To test this claim, we have him attempt 50 free throws. He makes 32 of them. Notice, remember, in hours, he made 27, so even less than that, right? So um, if we use software to simulate 400 sets of 50 shots, assuming that the player is really an 80% shooter. So if we take an 80% shooter and have 400 different samples of 50 shots, notice this right here is our distribution of a p hat of our sample. So p hat 0.64 um, or lower was only observed 3 times. Those 1, 2, 3 dots, right? And in our case was actually, even if you look at it even further, our p hat was 54%. So 0.54. If you look at 0.54, that's all the way over here. So there's none over there. So in our case, we can even have a stronger conclusion, because zero times in those 400 samples would that have happened. But in this data here, where it happened 32 out of 50 free throws, it could happen 3 out of 400 times, or 0.75% of the time. So again, highly unlikely, and in our case, very, very, very unlikely. If 400 people who make 80% never shot that low, um, then it's highly unlikely our guy shoots 80%. So the observed statistic is so unlikely if the actual parameter is p equals 80.8, that it gives convincing evidence that the player's claim is not true. So a lot of times there are two possible explanations for the fact that he only made 64% of his free throws. First, the null hypothesis is correct. The if like that the player actually does make 80%, and just by chance a very unlikely outcome occurred. So I mean, it's always possible that he just went on a real big streak of bad luck or something like that. But um, uh, the other explanation is that the alternative hypothesis is correct, that the population proportion is actually less than zero point 0.8, so the sample result is not an unlikely outcome. So the basic idea is that an outcome that would rarely happen if the null hypothesis were true is good evidence that the null hypothesis is not true. So in this case, it was very, very unlikely that he would make 32 out of 53, or even less likely to match our numbers of 27 out of 50. And so that makes it highly likely that the null hypothesis is false. So we would reject the null hypothesis. And we see that when we see the actual probability um, that the computer was using to calculate these, it was 55%. We see that we were correct in rejecting the null hypothesis. So the null hypothesis states the claim that we are seeking evidence against. The probability that measures the strength of the evidence against the hypothesis is called a p-value. And this is the p-value I was talking about before when I talked about something that is kind of rampant in research these days, especially corporate-backed research. Like if, I don't know, Dole wants to make a claim that oranges prevent cancer or something like that, and they fund research to that effect. A lot of times that research will be very biased, and they'll use these techniques to show a result that's not necessarily true. All right. The probability computed assuming H naught is true, that the statistic would take a value as extreme or more extreme than the one actually observed, is called the p-value of the test. So like in the previous case, using the numbers that we have right here, there was 0.0075. That would represent our p-value, because the chance of what happening was, or worse, was 0.0075. So that would be the p-value in this case. Small p-values are evidence against H naught, because they say that the observed result is unlikely to occur when the null hypothesis is true. So again, if it's highly unlikely that the event would happen, then it's evidence that the null hypothesis is incorrect. Large p-values fail to give convincing evidence against H naught because they say that the observed result is likely to occur by chance when H naught is true. So again, if I had ended up with, out of our 50, we ended up making 40 of them, well, that would be a value of zero point 0.8, and that would be this guy right here. Well, that's a highly likely result. So if he shot 80% on his 50 shots, that's not convincing evidence that he's not an 80% shooter, right? We would take that as evidence that he actually is an 80% shooter. The final step in performing a significance test is to draw a conclusion about the competing claims you are testing. We make one of the two decisions based on the strength of the evidence against the null hypothesis and in favor of the alternative hypothesis. So we reject the null hypothesis or fail to reject the null hypothesis. Notice, a fail to reject the H naught decision in a significance test does not mean that H naught is true. For that reason, you should never accept H naught or use language implying that you believe H naught is true. So you always say you rejected it or you failed to reject it. Not reject or accept, reject or fail to reject. So if our p-value is small, we reject. If our p-value is large, we fail to reject. Now we'll talk about what does that mean, small and large, here in just a second. There is no rule for how small a p-value we should require in order to reject the null hypothesis. But we can compare the p-value with a fixed value that we regard as decisive, called the significance level. This is printed wrong for some reason. That's alpha, the Greek letter alpha. So if the p-value is smaller than alpha, we say that the data are significant at level alpha. In that case, we reject the null hypothesis H naught and conclude that there is convincing evidence in favor of the alternative hypothesis H sub A. So when we use a fixed level of significance to draw a conclusion in a significance test, if the p-value is less than alpha, we reject the null hypothesis. So that means it's likely we have convincing evidence for the alternative hypothesis. If the p-value is greater than or equal to A, we fail to reject the null hypothesis, so there's not convincing evidence for our alternative hypothesis. So let's take a look. Um, let's try and keep the answer hidden here. So a company has developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects an SRS of 15 new batteries and uses them continuously until they are completely drained. The sample mean lifetime is X bar equals 33.9 hours. A significance test is performed using the hypotheses mu equals the null hypothesis is mu equals 30, and the alternative hypothesis is that mu is greater than 30. So, where mu is the true mean lifetime of the new deluxe AAA batteries. The resulting p-value is 0.0729. So again, that's the probability that we would have gotten, or not really the probability, that's not quite the right word, but if we did a bunch of samples, we would end up with X bar being 33.9 or higher in about 0.0729. So about 7.3% of the samples. So what conclusion could you make for each of the following significance levels? Justify your answer. So if alpha is 0.1, is the p-value larger or smaller? Well, it is smaller, and so we would conclude that yes, we think we would reject the null hypothesis, right? Because we think we have convincing evidence that the alternative hypothesis is accurate. However, if alpha equals 0.05, we would fail to reject the null hypothesis because the p-value is bigger than alpha. So let's take a look at the answer. And so again, yeah, we reject the null hypothesis if alpha is 0.1 because the p-value is less, and that gives us convincing evidence that they do last longer than 30 hours on average. But if we let alpha equal 0.05, we fail to reject because we do not have convincing evidence. And what level that is again kind of like you can kind of think of the alpha value as being similar to the confidence level that we were talking about before when we were talking about confidence intervals. All right, so, and then finally, the exam tip, the conclusion to a significance test should always include three components: an explicit comparison of the p-value to the stated significance level. So we compared, we said it's less than um, alpha equals zero point 0.1. You need to have that component. A decision about the hypothesis, reject or fail to reject. So we reject the null hypothesis, and then a statement in the context of the problem about whether there is convincing um, evidence for the alternative hypothesis. So we have convincing evidence, and the alternative hypothesis was that they lasted longer than 30 hours. So we have convincing evidence that the company's batteries last longer than 30 hours on average. All right. So type 1 and type 2 errors. So these are kind of like, I don't know, false positives and false negatives, but if you're familiar with those terms. But when we draw a conclusion from a significance test, we hope our conclusion will be correct, but sometimes it will be wrong. There are two types of mistakes we can make. If we reject the null hypothesis when it is actually true, we have committed a type 1 error. If we fail to reject the null hypothesis when the alternative hypothesis is true, we've committed a type 1 error. So um, let's take a look at that a little bit further. So the probability of a type 1 error is the probability of rejecting the null hypothesis when it is really true. And this is exactly the significance level of the test. So the probability of type 1 error in this one that we just did here, when alpha equals 0.1, the probability of a type 1 error is exactly 0.1. Similarly, in part B, the probability of type 1 error is 0.05. So if we pick a smaller number, that makes it less likely that we have a type 1 error. So consider the consequences of a type 1 error before choosing a significance level. So the reason why I mentioned that is it depends on what scenario we're talking about. There are some cases, like it's kind of similar to the tank problem, where it would be much better to overestimate the number of tanks than underestimate and go in and get crushed. Same type of thing. It depends on what we're talking about. Whether, like, if there's a drug that has, that might help your blood pressure, but has a small risk of very, very significant side effects, you want to be absolutely certain that it does what it says it does before prescribing it. Because if your potential side effects include death, well, you don't want to be taking a medicine that actually doesn't make any difference. So there are times where you'd want to have alpha where be very small, and sometimes where you don't have to have it quite as small. So let's just do an example here. So a potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. To make the decision, a supervisor will inspect a random sample of potatoes from the shipment. The producer will then perform a significance test using the hypotheses. The null hypothesis is that P equals 0.08, so that's the proportion of all the potatoes is 0.08. And the alternative hypothesis is that the proportion of all potatoes with blemishes is greater than 0.08. So, um, describe a type 1 and type 2 error in this setting. So remember, uh, so if we reject the null hypothesis when it's actually true. So when we think about this, that would be the case where we say no. There's evidence that there is more than 0.08. More than 8% of the potatoes have blemishes, but it turns out the actual proportion in the shipment is 8% or less. So, and a consequence of that is we would reject the shipment when the shipment would have been would have been a suitable shipment for our potato chips. So, and then that might add time to get another shipment, and the supplier of the potatoes would lose money on that as well because they had a perfectly good shipment that got rejected because of of a type 1 error. A type 2 error would be one where we fail to reject the null hypothesis, so we accept the shipment, but it turns out a lot more than 8% of the potatoes have blemishes. So in that case, the potato maker accepts the shipment when they probably shouldn't, and they might have unhappy customers or something because the a lot more of the potato chips have blemishes in them than otherwise would have happened. So let's see what the book actual test is. Um, and a nice thing is fail to goes with type 2. That's a nice way to keep them straight. So um, if you fail to reject, that means it's a type 2 error. So if you fail to reject when you should reject, that's when that happens. And so it looks like you can read through this, and those are the two types of errors. So continuing with this example, let's take a look at um, uh, suppose that the potato chip producer decides to carry out this test based on a random sample of 500 potatoes using a 5% significance level. So alpha is 0.05. So um, type 1 error is to reject the null hypothesis when the null hypothesis is actually true. So if our sample results in a value of p hat that is much larger than 0.08, we will reject the null hypothesis. How large would p hat need to be? The 5% significance level tells us to count results that could happen less than 5% of the time by chance if h naught is true as evidence that h naught is false. So basically what we're saying is we only want a type 1 error 5% of the time, right? So 95% of the time we're not going to have a type 1 error. All right, so we need to figure out um, what p hat should be. Basically, you can think of it as how many potatoes can be bad in our sample of 500 potatoes before we reject it. So shape. This is approximately normal because remember the rules. Like if when we're talking about population proportions, we just take n times p and n times 1 minus p, and if they're both at least 10, then it's going to be approximately normal. So we notice we get 40, we get 460, so they're both at least 10, so it's approximately normal. The center is at 0.08, which right, mu sub p hat, which is equal to the population proportion, so 0.08. And our spread, again, from our formula sheet, we get 0.01213, assuming that there are at least 5,000 potatoes in the shipment, which I think is a reasonable assumption, right? If we're a potato chip supplier, you probably get a lot more than 5,000 potatoes in a single shipment. So let's take a look at um, what p hat should be. So if we basically want to figure out where does in our calculator, remember it's always area to the left, so you want to know when there's 5% of the area is to the right. So that means 95% is over here and 5% is over here. And so when we do that, so we want 0.95, mu is 0.08, and sigma is 0.01213 from what we calculated above. When we do that on our calculator, we get 0.09995, which they round to 0.10, which is very reasonable. So the values of p hat to the right will cause us to have a type 1 error, right? Well, we would reject it. We'd say, oh, we don't believe you that there's 8% in this shipment are blemished. We think there's more than that. So um, a type 1 error happens anywhere to the right of p hat equals 0.1. So, and this will happen in 5% of all possible samples. So um, realistically, if we look at it, if we have more than 50 bad potatoes in our sample of 500, then we would reject the reject the shipment. And that basically wraps up our um, video on section 9.1. So the basics of significance tests is we need to state. We learned how to state the null and alternative hypotheses for a significance test about a population parameter. Interpret a p-value in context, right? A p-value is basically how likely it is that the null the null hypothesis was true, um, uh, and we got the given result that we did. Determine whether the results of a study are significantly statistically significant and make an appropriate conclusion using the significance level. So again, we just did that based on alpha. And then type 1 error and type 2 error. Remember, fail to means type 2. So if we incorrectly reject the null hypothesis, that's a type 1 error. If we fail to reject the null hypothesis when we should have, that's a type 2 error. and we gave a consequence of each.